Hello, hello, my dear friends. Hi, Shubhankar. Hi, Akshara. Hi, Yashwant. Hi, everyone. Hello, everyone. Hi, Aditya. Hi, Amit Dubey. Hello, my dear friends. Hi, Shubhankar. Hi. Hi. Hi, Yashwant. Hi. Still anyone is in live? Still anyone is in live? Still anyone is in the live? Just say me hi. Right. Now, now I'm starting the class. Right. My dear friends, up to where we done in the last class? In the last class, we have seen how the overlapping will be happen. Now, in that overlapping, the last class we have discussed up to which one? The overlapping, right? Now you can see. Now the PZ orbital. Hi, Sri Ganesh. Hi. Now PZ orbital, internuclear axis Z leads to give the sigma bond, right? Next to PX orbital, PY orbital. Hi Aditya. If the internuclear axis Z, that leads to give the no bonding, because if the internuclear axis PX and the PY are perpendicular to each other, that we have seen. Next, if the internuclear axis is Y, PX orbital leads to give the pi bond, right? This we have seen. Now, here based on this yes, 9:30. My dear friend Asterisk, today 9:30. 9:30 will start the class. 9:30 will start the class. Now, right now, here based on the this overlapping concept, how the sigma bond and the pi bonds are forming in the molecules, now we are going to see. Now, first, according to the according to the VBT, according to the VBT, amines only. According to the VBT, will unpaired electrons will form the bond. Clear? This is a one key point you have to remember. According to the VBT, unpaired electrons will form the bond, right? Now, here based on this point, now what are the unpaired electrons? Now, if you take the p orbital or p subshell, we are having the three p subshell, we are having the three orbital. Now, in this three orbital, if suppose the orbitals are in this manner. Now, these are the unpaired electrons. These are the unpaired electrons. These unpaired electrons only will form the bond. Now, the completely filled orbitals will not form the bond. Clear? Now, these electrons which are not participated, the electrons which are not participated in bond are called as lone pairs. Right? Then, if any electrons are not participated in the bonding, that we call it as a which one? Lone pairs. Right? Clear? Then, if any this unpaired electrons only will form the bond. Now, based on this concept, how the bonds are forming in the O2, now we'll see. Clear? Now, how the bonds are forming in the O2, now we'll see. formation of O2, right? A formation of bonds in O2. Now, the formation of the bonds in the O2, one oxygen and the one oxygen. Now, the electronic configuration of the one oxygen, only the valency electrons will participate in the bond. I explained very clearly. Now, that it is having the helium 2s2 2p4. Now, helium 2s2 means 2s2 we are having the completely filled, and the 2p4 only we are having only the two unpaired electrons. Now, another oxygen, here it is a helium 2s2 2p4, right? Here we are having the two electrons. Now, here we are having the 2p4. Now, we know the internuclear axis, along the internuclear axis orbital will be overlapped. So, the internuclear axis I was taking it as a Z, right? Now, this is a, let's suppose if you take this as a px, this is a pz, and this is a py. Now, this is a px, this is a pz, and this is a py, let us assume, right? Now, we know for the pz orbital, py and px are perpendicular, right? Now, here one oxygen, p subshell we know, p subshell, the shape of the p subshell will be the dumbbell. Now, one oxygen in this pz orbital, we are having one electron. Now, another orbital, pz orbital also we are having the one electron, right? Now, this two will be overlap along the internuclear axis. Now, if the orbitals are overlapping along the internuclear axis, leads to give which bond, my dear friends? Now, this is the internuclear axis Z. This is the internuclear axis Z. If the internuclear axis Z, pz orbital along the internuclear axis Z overlaps, leads to give which bond? Overlaps leads to give which bond? Overlaps leads to give which bond? Good, Akshara, good. Now, it leads to give the sigma bond, right? Now, for this sigma bond, oh, good. I have many friends. May I know who is this? I have many friends. May I know his name? Now, good, Vaishnav, yes, sigma bond. Right. Now, next one for the pz orbital. Good, Yashwant, good. Now, for this pz orbital, now, py orbital. Good, Akshara, sorry, good, Subhana. Now, for this pz orbital, now, py orbital is perpendicular. For the pz orbital, now this py orbital is perpendicular. Now, for this pz orbital, py orbital is perpendicular. Now, this is a py orbital. Now, py orbital also we are having the one electron. Now, these two sideways overlaps leads to give the pi bond. Now, you can see here this one orbital, px orbital, has not participated in the bonding, and here the one 2s orbital is also not participated in the bonding. If the electrons are not participated in the bonding, we call it as a lone pairs. Yes, good. Now, this we call it as a lone pair which has not participated in the bonding. We call it as a lone pair. Now, we'll see the oxygen, how the bonds are forming in the oxygen. Oxygen, we are having the two lone pair of electron. One is of the 2s orbital, one is of the which one? Px orbital. Next, another oxygen also we are having the two lone pair of electron. Then one it is a sigma bond and one it is a pi bond. One it is a sigma and one it is a pi. Now, this sigma bond is formed by the overlapping of pz. Now, this pi bond is formed by the overlapping of which orbital? Py. Now, in this manner, now the formation of the one sigma bond and one pi bond in the O2. In this manner, the one sigma bond and the one pi bond is forming in the O2. Now, we'll see formation of bonds in the N2. Formation of bonds in the N2. Now, the N2, one nitrogen contain helium 2s2 2p3. Now, 1s contain 2 electrons and the p contain 3 electrons, right? Now, another nitrogen also contain 2s2 2p3. 2s2 2p3, right? Now, here internuclear axis, we are taking it as a Z. Now this is a PZ, this is a PX, this is a PY. PZ, PX and the PY. Right? Now one PZ orbital. Now you can see this is one PZ orbital. We are having the one electron. Hello Jasmine, hello. Good evening, good evening. Now another PZ orbital. Another PZ orbital, we are having the one electron. Clear? Now this is of the PZ orbital of one nitrogen. This is a PZ orbital of one nitrogen. Clear? Now PZ orbital along the internuclear axis Z leads to give the sigma bond. Right? For the PZ orbital, PX and the PY are perpendicular. Hi Sham. Hi. Now for the PZ orbital, now one PX orbital is perpendicular. Now for the PZ orbital, one PX orbital is perpendicular. Now this PX orbital sideways overlaps leads to give the pi bond. Next one. Yes. Good. Good Ashwin. Now again for the PZ, one, this is PY, right? This is PY. Now this is a PZ orbital. Now this is a PZ orbital. Now the PY orbital is also perpendicular to each other. Now one PX orbital is also perpendicular to each other in this manner. On the PX orbital. Now this is a PX orbital. Now PX orbital sideways overlaps leads to give the pi. Sideways overlaps leads to give which one? Pi bond. Now we'll see the formation of the N2, how the bonds has formed. Now in the formation of the N2, one lone pair of electron, right? Now one lone pair of electron and three bonds. Now this is the one sigma, one pi. Now this is the formation of the bonds in the which one? N2. Now one it has formed by the PZ. Next another it has formed by the PX. Another it has formed by the PY. In this manner the bonds are forming in the which one? In the N2. Next the another type of the one type of the bond it is forming. Now another type of the bond that we are going to see, that is now another type of the bond that we are going to see, that is a delta bond. Now actually this is this delta bond they are asking for the mains. Here now how the delta bond will be formed? Now the delta bond will be formed by the, if you take any dxy orbital. Now how the dxy orbital will be there? This is a dxy orbital, or dxy orbital or any dxy or dyx or dzx orbital. Now this is the lobes, right? Now these are the dxy orbital, right? Now exactly the same direction again we are having the, this is the one dxy orbital, right? Now in this dxy orbital, here exactly backward to it means, now if I keep it here exactly backward to it, right? Now in this manner when the dxy orbital when they overlap in this manner, that leads to form which orbital? That leads to form the delta bond, right? Now how the delta bond is forming? Here same one dxy orbital, another dxy orbital, when they overlap in this manner, that leads to form the delta bond. Clear? Now in this manner dxy orbital overlaps leads to give the which one? Delta bond. Right? Okay, my dear friends, it is not on the basis of the, I was not here to get anything, just for the student success I was here. I was not here for the views, or I was not here for the any money, or I was not here for the any fame. Just the students who are serious to their studies, I am ready to help them. That's it. Now the strength of the bonds, if they ask, sigma bond is a more strength. Then after the delta bond, then after the pi bond. Now this is the strength of the bond. This is the strength of the bonds. Clear? I hope it is clear for you. I hope it is clear for you. Anyone still having any confusion? Anyone still having any confusion? Clear? No. Next. Which one, Jasmine? Which one I was to explain? Which one I was to explain? Which one I was to explain? Which one I have to explain? No. Delta bond is not there for the NEET. Delta bond is only for the mains and the students who are preparing for the advanced. Actually, the dxy orbital will be in this manner. Now you can see the dxy orbital will be in this manner. Now in this dxy orbital, the same exactly backward to the same dxy orbital. When these two are overlapping, that leads to give the dxy orbital, or that leads to give the delta bond. Okay. Now the dxy orbital will be in this manner because these are the lobes and here it will be the axis. Here it will be the axis. Like here if it is a z axis, if this is a z axis, clear, and here it will be the x axis, the same another dxy orbital. Now, which backward direction, the same it will be overlaps leads to give the delta bond. Actually, the 3D molecule showing in the 2D, it will make somewhat difficult. Okay. Just you remember dxy orbital leads to form the delta bond. Okay. Right. Next, VBT has not explained about the shape of the molecule. Clear? Now the VBT, when the bonds are forming, now it has not explained the which one? Shape of the molecule. Clear? Now when it is not explaining the shape of the molecule, now the another concept, which one? Hybridization. Hybridization has explained the very beautifully about the shapes of the orbital. Very beautifully it has explained about the which one? Shapes of the orbital, it has explained very beautifully. Now the next concept that we are going to study, that is hybridization. Which one? That is hybridization. Right. Now what is the meaning of the hybridization? Now what we are going to see in this hybridization, whether the molecules are hybridizing or not, we don't know. Actually this is completely theoretical, I mean hypothetical concept. Whether the molecules are doing the hybridization or not, we don't know. But this hybridization will provide the what? Geometry and the shape of the molecule. Very clearly. Clear? Now why this hybridization it has came? Now why the VBT, whatever the VBT it has explained, why it has become failed? Because here, if you see it for the CH4, now according to the VBT, VBT has said that unpaired electrons will form the bond. It has said. Then for the carbon, if you take carbon, it is having 2s2 and 2p1. Now it is having the two unpaired electrons only. Then according to the VBT, carbon should form only the two bonds. Carbon should form the only two bonds. But we are seeing now the carbon here in the CH4, it is forming the four covalent bonds. Now you can see here it is forming the four bonds. But how? How the carbon is forming the four bonds? Now that it was explained by the concept called the hybridization. Clear? Now how the hybridization has explained that carbon is forming the four bonds means, now we'll see. Here ground state electronic configuration of the carbon, if I write, it is having the 2s2 and 2p2 electronic configuration. This is the electronic configuration of the ground state electronic configuration of the carbon it is having. Now due to that, when the carbon, this central atom, when the four hydrogens are approaching to form a bond with the carbon, this carbon has provided the two orbitals to form the bond like this, right? When it has formed the, for these two hydrogens, when it has gave the orbitals to form the bond, remaining these two hydrogens which has not participated, in the bonding, what it will do, it will also want to form the bond with the carbon. But these hydrogens, what it will do, it will repel this hydrogen. Means repulse means it will not allow these unbonded hydrogens to form a bond with the carbon. Which one? Carbon. So due to that repulsion, what happens? Energy released. Due to that repulsion, due to unbonded hydrogen repulsion, energy released, right? Now that released energy will absorbed by the central carbon. Now this central atom carbon will absorb that, which one? Will absorb that energy. When it has absorbed that energy, what happened? Now the electron which is present in the S will be absorbed by the carbon and excite one electron of S to empty p orbital. Clear? Now that the electron which is present in the S, it will be excited to the empty p orbital. Now we are going to see. Now we are writing excited state electronic configuration. So the excited state electronic configuration of the carbon will be 2s and we are having the 2p3. In this manner, 2s and the 2p3. Hi Anjali. Clear? 2s and the 2p3. Now we can see. Now here how many orbitals we got? Now the 4 atomic orbitals we got. But these 4 atomic orbitals, right? Now these 4 atomic orbitals, here this 2s is having the different energy and the 2p is also having the different energy. Because 2s, n plus n value is 2. Because here 2 and L is 0. But the 2p, n plus L value is 2 plus 1, that is 3. Now the orbitals, when they are forming the bonds, all should have the same energy, right? All should have the same energy. So to make the energy same, to make orbital energy same, we have to intermix. Intermix. Now this intermixing of atomic orbitals leads to give the new hybridized orbitals. new hybridized orbitals. Clear? How the intermixing of atomic orbital leads to give the new hybridized orbitals? How? Because now we know this is a s orbital. S orbital is a spherical. Now here it is a p orbital. P orbital is a dumbbell. P orbital is a dumbbell. Right? In this manner, the p orbital will be there. But when we intermix this 4 orbital to make their energy same, now we are getting the new hybridized orbital. Now the new hybridized orbital will be in this manner. One lobe will be higher and another lobe will be smaller. One lobe will be higher and another lobe will be smaller. One lobe will be higher and another lobe will be smaller. One lobe will be higher and another lobe will be smaller. Now these are the hybridized orbital. Each hybridized orbital we are having the 1 electron. Each hybridized orbital we are having the 1 electron. Clear? Now after getting these hybridized orbitals, each hybridized orbital should arrange themselves in such a way that those should be free from the repulsion. Enduko? If these electrons are nearer to each other, they will get repelled. Why? Electron is negative charge, electron is negative charge, negative charge. So those new hybridized orbitals should be arranged themselves in such a way that it should be free from the repulsion. So at what bond angle if they arrange, they are free from the repulsion. Now if these 4 hybridized orbital, when they are arranged at the bond angle of 109 degree 28 minutes of the bond angle, when they are arranged, they are free from the repulsion. They are free from the repulsion, right? Each hybridized orbital we are having the 1 electron, right? Now hydrogen, we know hydrogen, the electron is present in the 1s1. S is spherical, right? Here the S is spherical. One hydrogen atom, here the S is spherical, one hydrogen atom, here the S is spherical, one hydrogen atom, here the S is spherical, one hydrogen atom. Right? Now here this hybridized orbitals, the bond angle we are having 109 degree 28 minutes. 109 degree 28 minutes. Due to that, now we got the carbon. It is forming the 4 covalent bonds in this manner at the bond angle of 109 degree 28 minutes. 109 degree 28 minutes. When they have arranged at the bond angle of 109 degree 28 minutes, now we got the shape called as a tetrahedral. The shape we call it as a which one? Tetrahedral. Tetrahedral. Right? Now we'll see the shape. How the tetrahedral it has came. Now we'll see. Now here this is a shape of the tetrahedral. Now you can see here these are the hybridized orbitals. These are the hybridized orbital. Now I will remove these hydrogens. Here now here we can see these are the 4 new hybridized orbitals. These 4 new hybridized orbitals should arrange themselves in such a way that it should be free from the repulsion, right? At the bond angle of 109 degree 28 minutes, when they have arranged, they are free from the repulsion. After that, in the s orbital, we are having the electron, right? Now this sp3 hybridized orbital and one s orbital electron. One sp3 hybridized orbital and one s orbital electron. One sp3 hybridized orbital, one s orbital electron. One sp3 hybridized orbital and one s orbital electron overlaps, and finally it leads to give the tetrahedral structure. Now in this manner the tetrahedral will be there. Clear? I hope it is clear for you. I hope it is clear. Or still you are having any confusion? I hope it is clear. Is it clear? Right. Now right. Okay, fine. Now based on this hybridization concept, by using this hybridization concept, now how the molecules are, how the atoms we got the shapes, and how the hybridization we got. Now first of all we have to know the rules for the hybridization. We have to know the rules for hybridization. Rules for the hybridization. Okay, good, everyone, good. Now, rules for the hybridization. Now, what are the rules for the hybridization? First one, orbital have which one? Central atom provides required orbital to form hybridization. First one. Second one, orbital slight energy difference, it can undergo hybridization. Orbital with a slight energy difference can undergo hybridization. Clear? Done? These are the some. No. Next one. All the hybridized orbitals. Are identical in shape, comma, size and energy. Right? Now this is about the rules of the hybridization. Next, these very key point for the rule of the hybridization. That is, what is the very key point? Key point of the hybridization is these hybridized orbital should arrange in such a way that those orbitals should be free from the roots. Those orbital should be the free from the repulsion. Clear? These hybridized orbitals should arrange in such a way that those orbitals should be the free from the repulsion. Clear? Now, based on that one, now we are going to see the hybridization. First one, number of hybridized orbital, and this is a geometry. Now, how many orbitals intermixing leads to give the hybridized orbital means here the how many atomic orbitals are intermixing leads to give that hybridization. Let's suppose here the 1s and 1p are intermixing. 1s orbital and 1p orbital is intermixing. It leads to give the sp hybridization. So here 1s orbital and 1p orbital, 1s orbital and 1p orbital is intermixing leads to give the two new hybridized orbital. Now these two new hybridized orbitals should arrange themselves in such a way that it should be free from the repulsion. When they have arranged at the bond angle of 180 degree, those are free from the repulsion. Here, when these two new hybridized orbital arranged at the bond angle of 180 degree, those are free from the repulsion, and the geometry we got it as a linear. My dear, something I cannot see, I cannot read your name. My dear friend, the explaining in the Hindi, it is somewhat difficulty for me. I hope you will understand the English. Clear? Now we'll see. Now how the 1s orbital, 1p orbital, when they are intermixing, the s orbital, the p orbital intermixing, Now that those two new hybridized orbitals are arranged, you can see these two new hybridized orbitals are arranged at the bond angle of 180 degree. When they are arranged at the bond angle of 180 degree, now we got the shape called the linear. Now the bond angle between them, it is a 180. Clear? This is one hybridized orbital, this is one hybridized orbital. When they are arranged at the bond angle of 180 degree, those are free from the repulsion. Clear? Right, my dear friend, in the explaining of the Hindi, it is very difficult for me. I hope you will understand the English. Right, next one. Now, this is about the sp hybridization. Now, next we are going to see the how the sp2 hybridization will give. Now you see, sp2 hybridization. In the sp2 hybridization, one s orbital and one pz orbital and one px orbital. One s orbital, one px orbital, one px orbital overlaps leads to give the sp2 hybridization. Now these three atomic orbitals are intermixing now to make their energy same. Now we are getting through three new hybridized orbital in this manner. Now three new hybridized orbital in this manner. Now when these three new hybridized orbitals should be arranged themselves in such a way that it should be free from the repulsion, right? When they have arranged at the Now, when they have arranged at the bond angle of 120 degree, they are free from the repulsion. Clear? Now, each new hybridized orbital, when they have arranged at the bond angle of 120 degree, example for this one is the BF3. Clear? When they have arranged at the bond angle of 120 degree, now we got the shape trigonal planar. Now you can see here the three new hybridized orbital. Now one bond angle between them, it is a 120. When they have arranged at the bond angle of 120 degree, all are free from the repulsion. Clear? Now when they have arranged at the bond angle of 120 degree, now the geometry we got it as a trigonal planar. Right? Now the example for this one is a BF3. Next one, sp3. Just now we have seen how the sp3 it is forming, how the sp3 hybridization we got. Now one s and one px, one py and one pz. Now all these four atomic orbitals, when they have intermixed, now we got the four new hybridized orbital. When we got the four new hybridized orbital in this manner. Now these four new hybridized orbitals should arrange themselves at the bond angle of 109 degree 28 minutes. When they have arranged, those are free from the repulsion, right? Now you can see when they have arranged at the bond angle of 109 degree 28 minutes, those are free from the repulsion. Clear? Now when they are arranged at the bond angle of 109 degree 28 minutes, those are free from the repulsion. And the geometry and the shape, we got it as a tetrahedral. Now we have seen, right, just now, when they have arranged at the bond angle of 109 degree 28 minutes. Now we got the which hybridization? sp3 hybridization. Now here which hybridization we got? sp2 hybridization. Here which hybridization we got? sp hybridization we got. Right? Now here the bond angle is 120. Here the bond angle is 109 degree 28 minutes. Why not 90 degree? My dear friend, here if this 90 degree sp2, if they arrange it at the 90 degree, they are free. They are getting repulsion. What is the main point I said? Here this hybridized orbital should arrange in such a way that those orbitals should be free from the repulsion. So sp bond angle 180 degree, when they arranged, free from the repulsion. Free repulsion. Right? sp2 at 120 degree, free repulsion. Clear? Now in the sp3 at 109 degree 28 minutes bond angle, when they are arranged, only they are getting free repulsion. Right? Here in this bond angle only, if they arrange, they are getting the repulsion free. If you arrange at the 90 degree, again we are getting the repulsion. to minimize the repulsion, main criteria is that repulsion should be free from, right? Those orbitals should be free from the repulsion, right? That is our main criteria. Main criteria for it is orbital should be free from the repulsion, right? Is it clear, my dear friend, or still you are having any confusion? Next, the next type of the orbital we are having, that is one s and one px, one py, one pz and one dz square orbital when they have intermixed. Clear? Now here the 5 atomic orbitals are intermixing, right? Now this leads to give the sp3 dehybridization. In this sp3 dehybridization, we are having the one very interesting hybridization in the sp3d. Clear? 1s. Hello Chaitanya, hello. Now 1s, 1px and py. Hello Chaitanya, hello. Now these three hybridized are these three orbitals at 120 degree bond angle. It leads to give the sp2 hybridization. And now this pz orbital and the pz orbital and this dz square orbital at the bond angle of 90 degree, in the linear, they are forming the bonds. Pz and dz square orbital will form the one type of the bond, and s, px and py at the 120 degree bond angle as a sp2 hybridization, these are forming the one type of the bonds. Now in this sp3d hybridization, we are going to see the two types of the bonds, right? First, we are going to arrange these three hybridized orbitals in the 120 degree bond angle. Now, if you arrange at the bond angle of 120 degree, right? Now, these three new hybridized orbitals are arranged themselves at the bond angle of 120 degree in this manner. Then after that, one pz square and one dz square orbital we are having, right? Now, these two will be arranged in the bond angle of 90 degree in this manner, right? Here also one electron and one electron. Now this yellow color orbitals bond angle we are having the 120 degree, right? Now this white color and this yellow color orbitals bond angle we are having the 90 degree. If these orbitals are arranged at this bond angle is how much? When they have arranged at the bond angle of 120 degree and 90 degree only, those are free from the repulsion. Clear? Now we can see when they have arranged at the bond angle of 120 degree and the 90 degree, those are free from the repulsion. You can see here. Not this one. No. Here you can see. Here in these three we are having the three orbitals, right? Here you can see one orbital and this orbital are having the bond angle of 120 degree. This orbital and this orbital is having the bond angle of 120. This orbital and this orbital we are having the bond angle of 120. Now, when these orbitals are arranged at the bond angle of 120 degree and when they are here the 90 degree, when they are arranged in this bond angle only, those are free from the repulsion. If you arrange in any other bond angle also, they are getting the repulsion and they are unstable. See here that when the hybridized orbitals are arranged in the bond angle of 120 degree and the 90 degree, we are getting the free from the repulsion and we are getting this shape. And this shape we call it as this geometry or the shape we call it as trigonal bipyramidal. Geometry we call it. Clear? So the geometry what we got? Trigonal bipyramidal geometry sp3d at the bond angle of 120 degree and the 90. Next one, one s, one px and one py and one pz and one dz square orbital. Now one dx square minus y square orbital. Clear? Now total how many atomic orbitals are intermixing? Total 6, right? This leads to give the sp3d2. Clear? Now this 6 atomic orbitals should be intermixed. This 6 atomic orbitals leads to give the hybridized orbitals, right? Now this 6 hybridized orbitals Now these 6 hybridized orbitals should arrange themselves in such a way that it should be free from the repulsion. It should be free from the repulsion. Jaspin, I will explain with the one example PCl5 I will take and I will explain. Okay, once again I will explain the sp3d hybridization. Don't worry. With the I will take the one PCl5 example and I will explain. Wait that still that time you wait. Okay. Now these 6 new hybridized orbitals, when they have arranged at the bond angle of 90 degree, when they have arranged at the bond angle of 90 degree, clear? Now each the bond angle we are having the 90 degree. When these 6 new hybridized orbitals are arranged at the bond angle of 90 degree, now we got this shape. Right? Now you can see we got the shape in this manner. See, all the hybridized orbitals are having the bond angle of 90 degree. All the bond angles are having the 90 degree. See, all the bonds are having the 90 degree from down, from above. Clear? Now, when they have arranged at the bond angle of 90 degree, we got the geometry. When they have arranged at the bond angle of 90 degree, we got the geometry. The geometry we call it as a octahedral. The geometry we call it as a octahedral geometry we call it. Right? In this manner, the orbitals are intermixing leads to give the geometry. Now, with the examples, now we'll see how the orbitals, with the examples, how the hybridization is forming, how the orbitals are intermixing. Now, which geometry we are getting and what the bond angles we are getting out. First one we are taking the BeCl2. BeCl2 hybridization is sp. Now, example for the BeCl2 is sp. Now we know one s and one p orbital intermix leads to give the two new hybridized orbital in this manner. Now these two new hybridized orbital, when they are arranging at the bond angle of 180 degree, those are free from the repulsion. Right? Now here how these orbitals are intermixing, now we'll see. Beryllium ground state electronic configuration we are having. Helium 2s 2 and 2p is empty. Right? Excited state electronic configuration of the beryllium, if you write, one electron will be entering to the p. Now we are having the 2s and 2p, one 2s and one we are having the one 2p 1. Right? Now these atomic orbitals should be intermixed. These two atomic orbitals, one s and one p, when they are intermixing, we are getting the new hybridized orbital. When they are hybridized orbital, when they are arranged at the bond angle of 180 degree, those are free from the repulsion. Next one we are having the chlorine, right? Chlorine unpaired electron will be present in 3s2 3p5. It is present in the p orbital, right? Now the p orbital, this is the p orbital shape of the chlorine. This is the p orbital shape of the chlorine. Now this leads to give the BeCl. This leads to give the BeCl, and the bond angle we are having the 180 degree. Bond angle we are having the 180 degree, and the geometry we got it as a linear. Right? Next one. sp2. In the sp2 we are having the example of Bf3. Now boron we are having helium 2s2 2p1. Right? Excited state electronic configuration, if you write 2s1 and the 2p3, and these orbitals should be intermixed, leads to give the three new hybridized orbitals. Right? These three new hybridized orbitals should arrange at the bond angle of 120 degree, and fluorines we are having, it is present in the this fluorine, that unpaired electron will be present in the p orbital, we know. Right? Fluorine unpaired electron will be present in the 2s2, 2p5, right? It is present in the 2p5. Now this leads to give the BF3 at the bond angle of 120 degree, and we get the trigonal planar. Right? Next one, we are having the sp3, already we have seen, that is carbon. Ground state, we are having the helium, 2s2, 2p2. Right? Now excited state electronic configuration of the carbon, if you write, that we get the 2s1, 2p3. Now this we have to intermix. Now when we are intermixing, we got the 4 new hybridized orbitals. 4 new hybridized orbital. Now these 4 new hybridized orbitals, when they are arranged at the bond angle of 109 degree 28 minutes. Clear? My dear friend Ashwant, already I explained very clearly that hydrogen and fluorine will never ever act as central atoms, I said. When these two whoever will act as a central atom, how come the HF3 molecule will be formed, my dear friend? You have to say me. Okay? Now, then each hydrogen will have the H and H and here H and here H, and it leads to give the tetrahedral structure at 109 degree 28 minutes. Now tetrahedral structure, there is no any existence of HF3. Yes, Baudik, yes, live 9:30 we are having the live amines. 9:30 we are having the live, and the chapter is amines. Okay, now the next one, sp3d, example PCl5. Now phosphorus, ground state we are having the 3s2. Next one, we are having the 3d 3, right? 3d 3, and we are having the one vacant d orbital. Right? Now excited state electronic configuration, if you write, now this electron will be excited to the d, that is dz square orbital. Right? When we excited the electron, now here we are having the 5 atomic orbitals. Now these 5 atomic orbitals, when they have overlapped in this manner, this phosphorus, and here it is a Cl and here it is Cl. Now when they have formed the bond in this manner, here one is a pz and the dz square orbital. These two separately will form the at the bond angle of 180. At the bond angle of 180 in this complementing of sp hybridization, and this s, px and the py, when they are forming the bond of 120 degree bond angle, this pz and the dz square orbital, when they are overlapping, leads to give the bond at 180 degree bond angle. When they are arranged, they are free from the repulsion. Right? Now when the s and the px orbital, when they are arranged at the bond angle of one minute. Now here you can see, when they have arranged at the bond angle of 180 degree, here the Cl, here the Cl, here the Cl, here the Cl, here the Cl. Now those are free from the repulsion. Now what we got here, the two types of the bond we got. Now this pz and dz square orbital are forming the axial bond. Axial bond at a bond angle of 90 degree. At the bond angle of 90 degree. Next one, S, Px and the Py are forming the equatorial bond. Equatorial bond. Now these are forming the equatorial bond at bond angle of 120 degree. Clear? This I will write. This yellow color bonds are called as the equatorial bonds. Now white color bonds are called as the axial bonds. Now in the sp3d hybridization, this X, P, S, Px and the Py will form the equatorial bonds and the Pz and the dz square will form the axial bond. Two types of the bonds will be formed. Then only those are free from the repulsion. I hope it is clear for everyone. Then only those are free from the repulsion. If not, it is having the repulsion and that compound will be unstable. I hope it is clear for everyone. I hope it is clear for everyone. Now the next one we are having the sp3d2 hybridization. sp3d2 hybridization. Example is SF6. Now the ground state electronic configuration of the sulfur, if you write, it is having the 3s2, 3p4, right? And the 3d is empty. 3d is empty. Now excited state electronic configuration of the sulfur, if you write, 3s1, 3p3, and one electron will move to the one electron from the S and one electron from the P will move to the D. Total how many atomic orbitals we are having? 6 atomic orbitals we are having. This will be intermixed. This will be intermixed. Now total 6 atomic orbitals when they have intermixed at the bond angle of which one? At the bond angle of 90 degree when they have arranged, they are free from the repulsion. They are free from the repulsion. Now this SF6 will be arranged at the bond angle of 90 degree. Now in this manner, 90 degree when they have arranged, 90 degree bond angle. Now the geometry we got it as a octahedral. Octahedral, and the bond angle we are having 90 degree. Clear? And the next one we are having sp3d3. sp3d3 example is IF7. IF7. Now iodine, it is having the 5s2, 5p5. Clear? Now here the 5s2, 5p5 and the D is empty. D is empty. Right? Now the excited state electronic configuration, if you write, now the 5s1 and we are having the D, we are having 1, 2 and 3. Total how many orbitals we are having? 7 atomic orbitals we are having. This 7 atomic orbitals, this is the one special. You have to be very careful with this one, sp3d3. sp3d3, it is a very interesting. Now here the bonds, it will be arranged in such a way that it should be free from the repulsion, right? When they are arranging at the bond angle of, when they are arranging, now this iodine will be arranged. Now here the 7, here the fluorine. Now here the one fluorine, here the one fluorine, here the one fluorine, and here the one fluorine. Now here is the one fluorine. Clear? Right? Now when they have arranged at this fluorine and this fluorine is having the bond angle of 72 degree. Now this fluorine and this fluorine is having the bond angle of 90 degree. Clear? Now here the bond angle we got it as 72 degree and 90 degree. And these bonds we call it as the axial bonds. These bonds, these 5 bonds which I was written in the pentagonal, those are equatorial bonds. Now these bonds which I was drawing in the yellow color, these bonds we call it as the axial bonds. Now the axial bonds are having the bond angle of 90. Now equatorial bonds are having the bond angle of 172 degree. And this geometry we got it as a pentagonal bipyramidal. Pentagonal bipyramidal. pentagonal bipyramidal geometry we got. I hope it is clear for everyone. I hope it is clear for everyone. SP, SP2, SP3, SP3D, SP3D2, SP3D3. Or still you are having any confusion? Now, next. Now, here we are going to see next type of the concept that we are going to see, that is valency shell, electron pair repulsion, valency shell electron pair repulsion theory. Valency shell electron pair repulsion theory. Now, here in the valency shell electron pair repulsion theory, if the repulsion number or steric number, if the hybridization number, that we call it as hybridization number, if you are getting 2, that is SP. If you are getting 3, that is SP2. If you are getting 4, that is SP3. If you are getting 5, SP3D. If you are getting 6, SP3D2. If you are getting 7, that is SP3D3. Clear? Done? Now, these are the hybridization. But here, why we are going to study the valency shell electron pair repulsion theory? Because now here one trick I will say. That trick, if you remember, now any molecules hybridization they have given, easily you can identify. Easily you can identify, but the trick will not be helpful for you in the helping of the molecular geometry. Molecular geometry, the trick will not be help, but the trick which I was going to say, that it will be helpful only for you identification of the hybridization and the number of lone pair of electrons on the central atom. That's it. See, if you want to find the hybridization and the number of lone pairs on this carbon, we are studying about the valency shell, right? Already I explained very clearly. Valency shell of electrons only will form the bond formation. Then when it comes to the carbon valency shell, we are having helium 2s2 2p2, right? It is having only 4 valency electrons. Right? Now write the valency electrons like this. Now hydrogen to complete its duplet electronic configuration, it requires 1 electron. Right? Now each, how many hydrogens we are having? 4 hydrogens we are having. 4 hydrogens you write in this one. So each bond represent the orbital. 1 s orbital. This is 1 p orbital, 1 p orbital, and this is 1 p orbital. So this hybridization of this CH4 is sp3 with 0 lone pair. sp3 with 0 lone pair. Now, next, if you go it for the nitrogen valency electrons are 5. 1, 2, 3, 4, 5. Now, each hydrogen will form the 3 bonds, right? Now you can see this bond represents S, this bond represents P, and this bond represents P, and we are having this lone pair of electron, and we are having 1 lone pair contain 2 electrons, and this also present in the hybridized orbital, and this represents the sp3 with and this represents the sp3 with 1 lone pair. 1 lone pair. Right? Now comes to the oxygen now. Oxygen valency electrons are 6. 1, 2, 3, 4, 5, 6. Now each hydrogen will form the single bond. Now this represents the S, this represents the P, and the remaining unbonded electrons we call it as a lone pair. This represents the P and this represents a P. Now H2O is also having the sp3 with two lone pair. sp3 with two lone pair. Now here, why the valency bond theory we are going to study? This central carbon hybridization is sp3. Now nitrogen hybridization is also sp3. Now oxygen hybridization is also sp3. In all the three cases, hybridizations are sp3 only. Then here, when we found the hybridization and the bond angle in the CH4, we got that 109 degree 28 minutes. But when we have seen the bond angle in the ammonia, we got the bond angle of how much? We got the bond angle of 107 degree in the ammonia. When we found the bond angle in the H2O, we got 104.5 degree. Means central atom is having the same hybridization. Central atom is having the same hybridization, but bond angles are different. Bond angles are different. Then why it is getting bond angle different? Because central atom, due to the presence of this lone pair and this bond pair, due to the repulsion, what I said, that hybridized orbitals should be arranged themselves in such a way that it should be free from the repulsion, right? Now this central atom, when it is having the lone pair of electron, to minimize that, what? To minimize that lone pair and the bond pair repulsion, now they have decreased its bond angle from the original sp3 bond angle. We have expected the bond angle should be 109 degree 28 minutes. But due to the presence of nitrogen lone pair of electron, if they have arranged at the bond angle of 109 degree 28 minutes, they are getting repulsion. To minimize that repulsion, they have decreased its bond angle to the 107 degree, then they have become the stable. Now, when it comes to the H2O, due to the presence of oxygen, two lone pair of electron, now still they have decreased its bond angle to the 104.5 degree. Is it clear? Done? Now, here, now we'll see order of repulsion. Order of repulsion. Now, order of the repulsion that we are having, lone pair repulsions are having higher, then lone pair bond pair repulsion, next bond pair repulsion. Now this is the order of the repulsion. Now the direct question they may ask from this order also, you have to remember, right? Now due to the lone pair bond pair repulsions, now bond pair repulsion, due to that what it is happening, geometry is also changing. Due to that geometry is also changing. Now for that one we are having the VSEPR theory, the geometry that we are having. If the sp, if they have given sp hybridization geometry that we are having linear and bond angle is 180. Now next sp2, if they have given sp2 geometry, we know that is trigonal planar, bond angle is 120 degree. Right, examples for the sp. Now we'll see how if the lone pair of electron, if it is present, how the molecular geometry is changing or geometry is changing. Now we'll see. If the sp2 they have given, example bf3 if they have given. Now we know bf3, how to identify boron, it contains 3 valency electrons. Now each fluorine will form the single bond. Now this is a s, this is a p and this is a p. Now this is hybridization is sp2 with 0 lone pair, sp2 with 0 lone pair. Now BeCl2 if they have given. Now beryllium, if it is having 1 electron and 1 electron, now this is a Cl and this is a Cl. Now this is S and this is P. Now this hybridization is a sp. This hybridization is a sp. Next one. If suppose SO2 they have given. Now the sulfur contains 6 valency electrons. Sulfur contains 6 valence electron. Each oxygen will form the double bond. Each oxygen will form the double bond. Why? Oxygen to complete its octet, it requires 2 electrons, right? So that's the reason one oxygen will take the 2 electrons from the central atom. So this is a S and this is a P, and one unbonded electron that we call it as a lone pair, and one lone pair contains 2 electrons. So this hybridization is a sp2 with one lone pair, sp2 with one lone pair. Clear? And the geometry we got it as linear, sorry, geometry we got it as a angular or bent, that we call it as a angular or bent. In this manner we will get the angular or bent for the SO2. SO2 shape will be in this manner, right? Next one we are having sp3. Next one we are having the sp3. In the sp3 you know, CH4 just now we have seen, that is tetrahedral, and the bond angle is 109 degree 28 minutes. Now when it comes to the NH3 just now we have seen, that is sp3 with one lone pair. Now when the sp3 with one lone pair, the bond angle when they have arranged at the 107 degree, now the geometry we got it as pyramidal shape. We got it as pyramidal shape. Now we'll see how the ammonia shape we got pyramidal. Now we'll see. Now the nitrogen, you can see this is a nitrogen with a one lone pair of electron. Here you can see this is a nitrogen, this is a nitrogen, and this is hydrogen, this is hydrogen, and this is hydrogen, one lone pair of electron. Now this is a pyramidal shape. You can see, I hope it is clear, this is a pyramidal shape. This is a V-shape pyramidal shape. Now next one. Now the next one we are having the H2O, right? H2O just now we have seen, that is sp3 with two lone pair. Now bond angle we are having, that is 104.5 degree, 104.5 degree, and the geometry we got it as a bent or angular, bent or the angular. Now this is a, see, this is a structure of the H2O. Now one oxygen, two lone pair of electron, and two bond pair. Now due to this two lone pair of electron, still the bond angle has been decreased. Actually, you can see, we have expected the hybridization should be in this manner. Which one? This carbon, this is a CH4. This carbon hybridization is sp3. Now here this oxygen hybridization is also sp3. But both the cases bond angles are different. You can see here the bond angle is 109 degree 28 minutes. But here the bond angle is how much? Here the bond angle is how much? Here the bond angle is 104.5 degree in the H2. But here the bond angle is 190. Because here this carbon does not contain any lone pair of electron, but this oxygen it contains the lone pair of electron. Due to the lone pair of electron, now bond angle has been decreased. Here there is no any lone pair of electron. Now the bond angle has been 109 degree 28 minutes. Now, good evening Praneeth, good evening. Now at the ending of the class you have came, but even though the ending of the class you have came, now at the correct time you have came. Now you see the tricks you have asked, right? Next one we are having the sp3d hybridization. sp3d hybridization we are having the PCl5. Now PCl5 phosphorus contain 5 valency. Now write the 5 valency in this manner. Now each chlorine will form the single bond. Each chlorine will form the single bond. Now this leads to give the 1s, 1p, 1p, and 1p, and this is a 1d. Now the hybridization we got it as a sp3d with 0 lone pair. sp3d with 0 lone pair. When the sp3d with 0 lone pair, geometry we got it as what? Trigonal bipyramidal, right? Trigonal bipyramidal we got. And the bond angle we know, that is 120 degree and 90 degree. Clear? And the next one, already we have seen about the PCl5. Next we are going to see, that is a SF4. Now SF4, now we know sulfur contains 6 valency. Now each fluorine will form the single bond, right? When each fluorine, when it is forming the single bond, now this is a S, now this is a P, now this is a P, and this is a P, and this is a unbonded electrons. One lone pair will contain 2 electrons, and this is present in the D. Because P subshell we are having only P orbital, we are having only 3 subshells, right? Now this hybridization will be sp3 D with 1 lone pair, right? sp3d with one lone pair. Now we'll see how the sp3d with one lone pair. Now this is a PCl file. This is a PCl file. Here the sp3d hybridization we have expected it should be in the trigonal bipyramidal at the 120 degree and the next one at the 120 degree and the 90 degree bond angle it should be there. But here in the SF4 we got the shape in this manner, that is seesaw or distorted tetrahedral. Now the SF4 shape will be in this manner. Now the SF4 shape will be in this manner. Clear? Now you may get a doubt. You may get a doubt, sir, why you have arranged this lone pair of electron only in the equatorial bonds? Why not you arranged these bonds in the axial position? Now if I was arranged this lone pair of electron in the axial position, now this lone pair of electron is repelling with the 1 bond, 2 bond and the 3 bond. Clear? Now this lone pair of electron if I put it in the axial position, now I was getting the 3 bond pair of repulsion. Now each orbital should be arranged in such a way that it should be free from the repulsion, right? Now if I see, if I was arranged this lone pair of electron in the equatorial position, now this lone pair is getting only 2 bond pair repulsion. Now the repulsions are free, right? When I was arranged at the bond angle, or when they have arranged this lone pair of electron in the equatorial, I was getting only 2 bond pair of repulsion. So less repulsions are I was getting when I was arranged the lone pair in the equatorial position, right? That's the reason. Now due to that its shape we got it as a seesaw or distorted tetrahedral. Or the geometry we got seesaw, right? Next one we are having the ClF3. Now ClF3 chlorine contains 7 valency electron, right? Each fluorine will form the single bond. Now here we are having the S, here we are having the P, here we are having the P. Now here we are having the 1 lone pair P and here we are having the 1 lone pair P. Now this hybridization we got it as a sp3d with 2 lone pair. sp3d with 2 lone pair. Now we'll see the sp3d with 2 lone pair. Now we got the SF4, right? Now here also now this is a just now we have seen that is SF4. Now the next lone pair of electron. Now the next lone pair of electron should be arranged at the equatorial position only, right? If I arranged at the axial position, if I arranged this lone pair in the axial position, now you see 2 bond pair and 1 lone pair repulsion we are having. So to minimize that repulsion, that lone pair should be present in the which one? Equatorial position only. Now this is the shape of the ClF3. Now due to that we got the T shape, right? Now you can see it is in the form of the T shape only. Now here the Cl and 2 lone pair. Here it is in the form of the T. You can see it is in the form of the T. So the geometry of the ClF3 sp3d hybridization with 2 lone pair, and that shape we call it as a T shape, and that shape we call it as a which one? T shape, right? And the next one we are having the I3 minus. Next one we are having the I3 minus. Now in the I3 minus, here the iodine valency electrons are 7, 1, 2, 3, 4, 5, 6, 7 and 1 negative charge indicates that 1 extra electron is added. Total how many? 8 electrons, right? Now here in the I3 minus, 1 iodine you have to take it as a central atom. 1 iodine take central atom. Remaining 2 iodines take it as bond pairs. Right? Now each iodine to complete its octet it requires 1 electron. Now here the 1 iodine, here the 1 iodine. Now you see this is a S, this is a P. Now this lone pair of electron 1p and this lone pair of electron 1p and this lone pair of electron it is a D. Now you see now the iodine will form the bond in this manner. Now it is having the 3 lone pair of electron, right? It is having the 3 lone pair of electron. One iodine contain 3 lone pair of electron. Now we'll see how the one iodine contain 3 lone pair of electron. Now yes, sp3d with 3 lone pairs. Now you can see here this is a T shape. Now just now we have seen. Now again the lone pair of electrons should be present in the equatorial position only. Now this is a I3 plus. Now iodine it contain the 3 lone pair of electron. Iodine it contain the 3 lone pair of electron. This is a one bonded iodine and this is a one bonded iodine. Now we got the which one? I3 minus, and the I3 minus shape is a linear, right? You can see the shape we call it as a linear. Now we got the linear shape, right? We got the linear shape. You can see this is a linear shape. Now the shape we got it as a geometry. We got it as a linear, right? Now next, the next we are going to see. Next we are going to see the sp3d2 hybridization. sp3d2 hybridization we are having the sf6. Now each sulfur we are having the 6 valency electron. Each fluorine will form the single bond. Each fluorine will form the single bond. Now each fluorine if it is forming the single bond, here the S, here the P, here the P, here the P, here the D, here the D. Clear? Now sp3 d2 with 0 lone pair, right? With a 0 lone pair, right? sp3 d2 with 0 lone pair we got. Yes. Good. sp3 d2 with 0 lone pair we got. And the geometry we already know, that is octahedral. Octahedral. Next one we are having sp3 d2 with 1 lone pair. If we are having sp3 d2 with 1 lone pair, that is XeOF4 if you take. XeOF4 or BrF5 if you take, right? Now here the XeOF4, one xenon contains 8 valence electrons. Xenon is a noble gas electronic configuration. It is having the 8 valence electron. Each oxygen will form the double bond and each fluorine will take the single electron from the will be taken from the each central atom. Now this is a S, this is a P, now this is a P, now this is a P, and this is a D, and one lone pair of electron. Now this is a sp3d. sp3d2 with 1 lone pair, right? sp3d2 with 1 lone pair. sp3d2 with the 1 lone pair, right? Now we'll see. Here we are having the what? Now this is a sp3d, right? Now normally this is a sp3d2. This is a sp3d2, right? This is a structure of sp3d2. Now in this sp3d2, all are 90-degree bond angle. We can arrange the lone pair of electron at any bond angle. Now if I remove this one, if I remove this bond pair and if I arrange this lone pair of electron, now what is the shape we got? Now this shape we call it as a square pyramidal. This shape we call it as a which one? Square pyramidal. Now you can see here this is a lone pair of electron you are seeing. Is it clear? Right. Now here this is a xenon. Now here it is a wait. I will take it here better. Here it is a xenon. Now here it is a one lone pair of electron. Now here it is a double bond O. Here the fluorine. 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 And here it is a one lone pair of electron. Right, in this manner we will get the, and this one we call it as a square pyramidal shape, right? Next one we are having, now the next one we are having XeF4. Xenon we know 8 valency electrons. Now each xenon will form the bond with the fluorines. Now here it is a S, here it is a P, here it is a P, here it is a P, and here the one lone pair of electron D, and here it is a one lone pair of electron D. Now here the hybridization we got it as a sp3d2 with how many lone pair? 2 lone pair of electron. Now sp3d2 with 2 lone pair of electron. Now how the hybridization and the shape will be there? Now we can see. Now if you remove the one electron here, Now we got the shape of the sp3d2 with a 2 lone pair of electron. Now this is the shape of the sp3d2 with a 2 lone pair of electron. You can see now it is in the form of the sphere planar. Now it is in the form of the sphere only, right? If you path the plane like this, here it is in the sphere only. It is in the form of the sphere. You can see here it is in the form of the sphere. It is in the form of the sphere like this. It is in the form of the sphere only, right? Right. Now the geometry we got it as square planar. We got it as a square planar, right? sp3d2 with a 2 lone pair of electrons, right? Now next, here we got the, now in this manner we got the one trick I was given very my dear friends. Now I will give you some examples. Now you have to very fastly you have to say me what is the hybridization and the number of lone pair of electrons. Now if any students, if you are seeing newly, try to comment your answers in the comment box. Okay, I will give you the some questions. Now what is the hybridization and what is the hybridization as well as its geometry? What is the hybridization and the geometry? If you know the answer, try to give me, and if you don't know, or if you are watching newly, or if you are watching after the live, just you give your answer of this one in the comment box. Can anyone say me the what is the hybridization and the geometry? Can anyone say me what is the hybridization and the geometry? Can anyone say me the what is the hybridization and the geometry for this one? Now this is the one. Now while you are commenting your answer, just you give the numbering and try to give the answer. Okay, this is the one, and say me the geometry as well as hybridization. Now the second molecule. No, sp3d with okay, sp3d with 3 lone pair, right, okay. Next one, XeF6 geometry and hybridization, second one. Yes, okay. XeF6, yes, okay, good. Next one, XeF6. Now the remaining who are in the live. Next, third one. XeO3. Fourth one, CH3 plus. Fifth one, CH3 minus. Sixth one, NH4 plus. Now the seventh one, we are having H3O plus. Now the eighth one, we are having I3 plus. Ninth one, sp3d3 with 1 lone pair. Okay. Subhana, you got it as a hybridization, that is sp3d3 with 1 lone pair. May I know the geometry? May I know the geometry of that sp3d3 with 1 lone pair? Ninth one, we are having, strong, we'll take it as a BCl3. 10th one, we are having may I know that what are the hybridizations? ICL. Now next one, 11th one, we are having the CHCl3. 12th one, we are having the NO2 minus. 13th one we are having the SO3. 14th one we are having the CO3 minus 2. CO3 minus 2. 15th one we are having the ClO4 minus ClO4. Now here almost 15 molecules I was given. Now this one I will say. Now this hybridization 1, 2, 3, 4, 5, 6, 7, 8, right? Done. Now this is the each fluorine will form the fluorine, 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 and the fluorine. Now this is a S, this is a P, this is a P, this is a P, this is a D, and this is a D, and this is the lone pair of electron D. And this one we are having the sp3 d3 with one lone pair. sp3 d3 with one lone pair. sp3 d3 with one lone pair. Now the geometry we are having distorted octahedral. Distorted octahedral and sp3 d3 with one lone pair. sp3 d3 with one lone pair. And the remaining, my dear friends, 3, 4, 5, 6, 7, 8 and the 9, 10, 11, 12, 13, 14, 15. I will see how many of you will be comment your answers, correct answers in the comment section. I will cross check. Okay. Now, my dear friends, I was ending the live by here. Oh, better. I will minimize my video. Now you can see. I hope you are going to see the videos now. Sorry, questions here. Now total almost I was given the some 15 questions. Now these 15 questions you can see. My dear friends, only the hybridization with number of lone pair. No need of molecular geometry. These questions, try to give me the answer. Try to give me the answer. Hybridization with number of lone pair in the comment section. Okay, my dear friends, anyone are having any concern, or should I end the live? Anyone are having any concern? Should I end the live? Only total these 15 questions. Total these 15 questions. Answers you just give in the comment box. Like only question number 3. I mean like 3 sp3d with one lone pair, like that. You just give your answers in the comment section. I will see how many of you will give the correct answer and who will give the first. I will see. Right? Should I end the live? Should I end the live or still you are having any concerns? Should I end the live or still you are having any concern? Should I end the live or still you are having any concerns? Should I end the live or okay. Hi Elaya, I am fine. In Bagunanu, nu Bagunava. How your preparation is going on? And my dear friends, if you are not having any concerns, you can leave the live. I mean, I was going to end the live. My dear friends, very fastly you have to give me the answers. I will see how many of you will give the correct answer in the comment section. The first comment will be pinned. I will pin your first comment. Good night. Okay. The one who has given the correct answer for all the 15, that first comment will be pinned. ఎల్లయ్య నీకు ఎక్కడెక్కడ ప్రాబ్లం అవుతుందో నువ్వు ఒకసారి నాకు నా మెయిల్ ఐడికి దిస్ ఇస్ మై మెయిల్ ఐడి. నువ్వు నీకు ఎక్కడెక్కడ ప్రాబ్లం ఫేస్ అవుతుందో నీ ప్రాబ్లమ్స్ అన్ని నా మెయిల్ ఐడికి ఒకసారి టెక్స్ట్ చేయి. I will talk with you. నీకు ఎక్కడెక్కడ ప్రాబ్లం అవుతుందో, ఎలా ప్రిపేర్ అవ్వాలి, ఎక్కడెక్కడ ఏం రెక్టిఫై చేసుకోవాలి అనేది నీకు క్లియర్ గా ఎక్స్ప్లెయిన్ చేస్తాం. ఓకేనా? నా మెయిల్ ఐడి ప్రొవైడ్ చేశాను కదా, ఆ మెయిల్ ఐడికి నువ్వు ఏదన్నా నీ డౌట్స్ ఏమన్నా ఉన్నా, సరే ఇక్కడ ప్రాబ్లం అవుతుంది, ఈ చాప్టర్ లో ప్రాబ్లం అవుతుంది, ఇక్కడ ప్రాబ్లం అవుతుందని నాకు చెప్పు. నేను ఆ మెయిల్ త్రూ నీకు కాంటాక్ట్ అయ్యి నీకు డౌట్స్ అన్ని క్లియర్ చేస్తాను. ఓకేనా? ఓకే మై డియర్ ఫ్రెండ్స్, ఐ వాజ్ ఎండింగ్ ద లైవ్. Bye. See you tomorrow. Bye, my dear friends. See you tomorrow. Should I end the live? నువ్వు నాకు నీ లైక్ నువ్వు నాకు నా ఈమెయిల్ కి నువ్వు మెసేజ్ టెక్స్ట్ చేయి, నేను నా నెంబర్ ప్రొవైడ్ చేస్తాను అక్కడ. ఎందుకంటే ఇది పబ్లిక్ కాబట్టి ఇక్కడ పబ్లిక్ గా నా నెంబర్ నేను ఇవ్వలేను. పర్సనల్లీ ఐ విల్ గివ్ యూ మై నెంబర్ అండ్ ఐ విల్ కాల్ యూ, ఓకే? ఆర్ యూ కెన్ కాల్ మీ, ఐ కెన్ గివ్ యూ మై నెంబర్. సరేనమ్మా? నౌ ఐ వాస్ ఎండింగ్ ద లైవ్ and we'll see you tomorrow. Still you are having any concerns, anyone who are in the live? Any concerns, any doubts? Any concerns, any doubts?